So let's get started. So we so last time was our first time to learn actual circuit about amplifier. And then I put some example, like I guess here's a lot of students are working on RF. So in RF they have a LNA, low noise amplifier, or and then this down converter is a mixer, and then I mean amplifier is everywhere. It's a buffer, and then we can also put a gain. Um, so well, amplifier is like the most basic circuits. And also there is a like a trade-off. So everything is trade-off. So most of the time, if we spend more power, then it shows a good performance, but we cannot do that. So there's a lot of trade-off. And so we learned about common source stage. Um, this is also widely used. And I'll just go quick because we have a lot of things in a LT-SPICE. And any questions? And then we also learned about like resistor load and then these three active loads. And so here's a problem set. You can just try it at home. I recommend you try this home. So well, as we discussed about midterm, so the assumption is that if you can solve the problem set in lecture, then you will get 100%. I'm not trying to give you like very difficult things, something like that. So I'll try to put very basic things, like for example, the derivation of GM. Those things are you will always use it in actual circuit design. So I'm gonna put those things in midterm. So um, I'll try to solve these things. And so LT Spice, I think last time we stopped at PMOS design. So can you guys turn on the LT Spice? So we'll do it. And so last week what we did was NMOS design with this ID 10 microamps and GM 100 microsiemens. But we're going to do exactly same thing with PMOS, and then we'll see how PMOS size will be like. Oh, by the way, any question about lecture? Okay, yeah. So PMOS. So can you guys try this one, this page? Draw a starting point is the same as NMOS. And then there's a Excel file I uploaded in our iCampus. So also, can you guys download that Excel file and then let me just briefly explain it? So I guess you guys are, well, I mean, maybe not ready yet, but so in okay, in design PMOS, here what we done was we make this schematic. And well, I mean, well, let's make this schematic and then run the simulation result. Once everyone got this simulation result, then I'll start. So let's take some time. 아, 네. I think lots of people finished it, so maybe I can just go for it. And then if you haven't done, you can follow it later. So here, with if you finish this simulation, either in LT-SPICE or anything, what you get is you got a data point here. So we got a slope, and slope is here. Like in this case, this is 8 milli. It's not milliamps. Um, it's like a square root amps. So anyway, we got a 8, and then we have x, and then we can also find this number, and this is the threshold, and then we are going to calculate this with our Excel file. So we got 8 from simulation, right? So let's come back here. So this is how you use that Excel file for calculation. There are overall 3 different type of numbers. First, given by user. For example, L is 180 nano. This is what we chose before designing. So the way how we choose L is it depends. It also depends on noise, or also it depends on mismatch. But at this moment, because we haven't learned about mismatch or noise, just pick a normal length. So for 180 length, nanometer for length is kind of a good starting point. So just set it as 180, and then W, this is also like just a random number, 360 nano. And then this green boxed number, slope, we just got it from simulation, right? And then also we got this green number, VGS and ID square root. We got this number. For example, here we have a slope, but we also have this point. Well, you can choose any points, um, but not like edge point at the boundary, but just in a normal like middle point or something. So we have that. We have this number point, and then the equation will calculate VTH. So this yellow box VTH is calculated by Excel. And then also this UPCOX over 2, this is also automatically calculated. So in our PMOS characteristic, by using this schematic, these two yellow VTH and then UPCOX over 2, that's our target. So that's our target to have. And then we'll move on to design. So try to get these two number. And let's take a few minutes. Maybe I can move on to next page. So you may wonder why are we doing it? Because when we design things, usually these are our kind of starting point. We start from how much current we're gonna flow, or maybe how much GM do we need, depends on like bandwidth or requirement gain. So with our this page characterization, so here what we get was BTH and then UPCOX over 2. So these two are what we got from our those characteristic schematic. And if we move on to our design goal, so assuming that we need this PMOS, so that's our kind of goal. And also with this given target, we can calculate VOV, which is overdrive voltage. So and then this is also very this is one of the most strongest constraint because the voltage operating point is like very important. So VOV turns out 200 millivolts. I think we can also get this equation value from in Excel. So when we back to this Excel file in design target, this red one is given by user. Like, oh, we want to make a PMOS that the current is 10 micro and then GM is 100 microsiemens. So just accept it. We will learn more. Why do we need this? How do we set this kind of GM target or ID target? We'll move there. But at this moment, just assuming that, let's say you're in company and then your boss asks you to make this PMOS. So if you get this, the rest of the number will be calculated by Excel. So VOV is simply calculated like this. And then also we can get this W over L. But we already assume that L is 180, right? So we will get a W by using this Excel file. So try it. And then again, our target here is that we want to get this designed W. That's our goal. We want to find the width of the PMOS. Well, anyone who doesn't have a Excel file, I think one guy doesn't have Excel file. Anyone who doesn't have Excel file? Oh, So I was supposed to give an assignment today, but I think we are not ready. So this assignment will go to next week. But you guys have a tape out. Well, I mean, we'll see. That's okay. We'll give you an assignment next week, and then we will finish it next week. So, okay, so let me just explain a little bit more. I mean, why are we doing this? So again, we tried to design PMOS, right? And then the target was 10 microamps, and then GM is 100 micro Siemens. Is that Siemens? Siemens, Siemens. So Siemens, um, that's kind of given value. In real circuit design, these values are given because of certain condition. So what we're doing here is that we want some starting point of the design. So let's say, so if someone give you this number, and how do you start? How do you design your PMOS? It's kind of out of nowhere. So we try to reduce the parameters. For example, here, okay, I'm gonna just use L 180. That's also kind of from your experience. Maybe if you design circuits in this 180, then you kind of get that feel like a feeling like what kind of L should I use. So usually when you design amplifier, you need a lot larger than this L. But at this time, let's just say L is 180. So for example, it's like this. Let's say this amplifier requires a lot of like the noise constraint is really tough. That can happen, right? When you design amplifier, because of the application, the noise of this amplifier should be very, really low. In that case, usually what we do is that we choose a large L. So it really depends on your application. If you don't care about noise at all, then we're not gonna use large L. Or there's the other reason that we have to choose large L, like mismatch. Let's say your amplifier requires a very high constraint on mismatch. So mismatch means, so amplifier usually working on differential mode. So amplifier has two inputs. So we're gonna learn that, but just assuming that there's a like a condition that mismatch. Mismatch means when you fabricate the chip, like let's say two MOSFET, and then let's say you just place them right next to each other. It's not the same because of the fabrication. Fabrication has a randomness. Even if you place them really close, there is a variation in maybe in terms of length or in terms of W. So you cannot make a identical MOSFET, but you can mitigate those mismatch. So that's what we call mismatch. Let's say, oh, I want this MOSFET as 2 micrometer width. That's what I want. But if you really fabricate the chip, it turns out it can be like 2.01 micrometer or something like that. So there's always a mismatch. And if your circuit is really vulnerable to those mismatch, then what you usually do is that you make a device large. If you make things really large, it's more better to mismatch. For example, if you make, let's say you make 1 meter of MOSFET, and then your requirement is that let's say 10%, that's what you need. 10% less 10% mismatch is what you need. You make 1 meter of MOSFET, and then 10% is what? 100, no, 10 centimeter, right? That's really easy. You're not gonna miss the 10 centimeter variation. So if you make things large, it's highly likely you get a accurate number in terms of ratio. So the analog circuit design is the same. If your circuit is really vulnerable to mismatch, one way to do is that you have to make it large. In that case, we have to get larger L, not 180. 180 is kind of small for 180 technology. Maybe you can have 2 micro or something like that. So those starting L point depends on your application. But assuming that, okay, just 180, just decided we 180. So what we got ID, our target current, and then we got GM, because someone just gave you this GM. You have to make this MOSFET as GM with 100 micro. I'll explain some example of this. Just accept it. We have to make MOSFET, PMOS with 10 micro and then 100 micro Siemens GM. And then we can also choose L, right? Depends on your application. Let's say, I want to use L 180. So now what? Now what we have? The only left design parameter is W. We got everything. We only have to decide W. And then this process is to choose that W. But actually there is another design parameters, VGS. So let's say, for example, okay, here, let's say we have this MOSFET. Well, it doesn't matter, it's NMOS or PMOS. Let's say this is W is 1 micro. And let's say W is 2 micro. And there is ground. And my question here is that, can we make 100 microamps MOSFET here? Let's just assume that, yes, we can make it. And how about here? Can we also make 100 microamps MOSFET? So this is an important point. So we have two different MOSFET, two different NMOS. What I'm saying is two different width NMOS. My question is, can we achieve a current 100 micro in both cases? Can we do that? Yes, we can do that by changing VGS. So we have two parameters here. We can choose VGS and we can choose W, right? So in MOSFET design, there's too many parameters. There's not a single answer. And then what we're doing here is that we want some starting point. We want some starting point to design a circuit. And then after that, what people do is a lot of iterations. We just have to run a lot of simulations. But at least by doing this, we can get a good starting point. So again, here, let's say this is VGS1. And what about VGS2? Which one is larger? VGS1 or VGS2? Can anyone answer? In this case, assuming that they both flow 100 micro, which VGS should be larger? One? Yes. Why? Yes, why? Why M1 needs larger overdrive? Yes, that's true. So that's how we design it. So because this M1 has smaller width, we need larger voltage to drive to flow this 10 micro. And then I'm not gonna say M1 is better or M2 is, it really depends on the situation. Sometimes M1 is better, sometimes M2 is. So in this case, VGS1 should be larger, right? It means that it consumes it really depends on maybe what kind of prior circuit drive this. Maybe the prior circuit, prior amplifier, prior stage, because there's usually multiple amplifier stages. Maybe the prior stage of amplifier, they like maybe lower VGS or something like that, right? So it really depends on the situation. So sometimes we have to choose M1, sometimes we have to choose M2. But in our example, you see this part, VOV. So if ID and GM is decided, then usually VOV is decided. So in this case, all we need is just W. So in this case, just W is still a single left parameter, design parameters. So I think we'll do it next time again, next week. I think it's good to spend more time here because this is like the most important part of this LT-SPICE design experience. So for example, once you can do CS amplifier design, then that's fine. We don't have to do common gate or source power or something. They're kind of similar, but I think the beginning of this is really important. So, and then here's the other example. In CS amplifier, let's just see how we design common source amplifier. So like this, design target. So let's say we need CS amplifier and our design target is C load. It's like load capacitance, right? Because after amplifier, there will be a following stage. And this following stage would have a capacitance, right? So if you say C load 1 picofarad, it doesn't mean that our load is actually a pure capacitance. It doesn't mean that. It's like, for example, here, when they say C load there, so it's like, and this is V out. There can be the other amplifier, right, as the output. And then we can see C in, right? That's C load. So this C load means what kind of following circuits do we have? So that's how we decide C load. And then also ID here. So ID is not like so it's more like ID. The way how we get the constraint is like the maximum ID. We shouldn't over 20 microamps or something. So usually amplifier is working well when you spend more power, but that's not what we do, right? Because there will be a lot of power constraint. It could be. So assuming, so these are how we start, and then the output swing. This is also very important part. The operating voltage, DC operating point is very important when we design a whole overall system. So when we design amplifier, we are not only focusing on one single amplifier. We have to care about following circuit. We have to care about driving circuit, and those all require a specific voltage range. So assuming these are like our target, and so we're gonna do it next week too. But I just give you a hint of how we do it. And then here, there's the frequency 3 dB and frequency gain bandwidth. Well, we're gonna learn this, but just I just want to give you what kind of the meaning it is. So this F3 dB, it's like how fast your amplifier is. So let's say your amplifier should operate in 1 gigahertz, then it requires a very high 3 dB bandwidth, something like that. So to get that, well, actually this choose the L, which is related to the current. Also there's the other one, gain bandwidth. This is very important parameters. So usually gain bandwidth is represented as like this here. So as I said, CL, this is kind of fixed value, right? Because this is the next circuit condition. So it's just of course we can discuss with them, but assuming the CL is fixed. And what we want is this gain bandwidth, this FG we don't have to understand it now, but we just need this value. When we use our amplifier in feedback system, this FGBW is takes a very important role. So now what we got? We got FGBW already, right? From design constraints. And then we got CL, right? So we got these two already given. So now we can automatically get a GM target. Does it make sense? So in our amplifier design, FGBW is given and CL is also given. Now GM is automatic. That's the only left. So we got GM target here. So in this case, for example, that's why in our PMOS design, the way how we start was GM 100 micro. So that requirement is given by like gain bandwidth frequency or something like that. So I think please finish this PMOS design at your home. And then once in next week, we'll finish this CS amplifier design. And then our assignment will be there. So basically our assignment will be just summarize what we've done in our in-person class. So I don't think you need a lot of extra time to do that. Okay. Yeah. So this week, please finish PMOS. Try it. And I think we're just one more thing. So in PMOS, what we've done is we designed the PMOS and then we got 140 nanometer, right? And then what I said here, here. So by using this one, our first starting from 360 nano width, we designed it. And then we got, and then our answer is 1400 nano. So we got this number. If we use this number, and then if we design and then just apply it, the value isn't there. So something's wrong with our design, and then the reason is that we get this 1400 nano by using 300 nano, 360 nano NMOS, PMOS. That doesn't make sense. So we get a characteristic of 1400 nanometer PMOS by using 360 nanometer PMOS. So they have a huge gap. So this is an important part. We got a characteristic from kind of too far size of PMOS. So that's why we got a wrong number. I mean, 1400 is the right number, but we got a wrong like slope or something like that. So what we have to do is we have to iterate again. So once we got this 1400 nano, we're repeating this job again. And then now we're like steadily going to our answer. And then the core reason for this is that PMOS is not linear device, which means that if you have 360 nanometer length width of PMOS, you cannot predict like what 1400 nanometer device because they are not linear. For example, if you have 1 micrometer of PMOS characteristic, you cannot predict 10 micrometer PMOS characteristic. It's not like just multiplying 10. It's not how it works. That's why we have to recharacterize the PMOS on its like width range. For example, if you can get a 500 nanometer of characteristic PMOS by using 360 nano, because they're kind of close, but not like 1400. They're too far. So that's why we have to repeat this. And then the reason is that the PMOS is not linear. Okay. So this is